So now, in a moment, we will have the last lecture of the school. I think that this school is kind of as a good wedding party where good wine is at the end, or even the best wine is kept by the host until the end. So I hope that everyone will enjoy next great talk by Florian. Okay, so 3 seconds for the slow people. And yes. So yeah, the stage is yours.
Thank you very much. So welcome back. Today I wanted to tell you about 2 examples out of our own research where we have applied reinforcement learning to quantum physics in situations that are kind of a bit tricky. So you have to think hard. How do you even set up the scenario? How do you formulate the reward and so on? But before I get to these 2 examples, I want to give a brief recap. That is the summary that we put up at the end of last time. So what are the advantages and disadvantages of having model-free reinforcement learning? So one of the advantages I mentioned was that you can not only do control, that is a sequence of actions that achieves a desired target, but you can do control with feedback. So the actions depend on what you observe, and depending on what you observe, you have to take one or the other actions. And the space of all feedback strategies is much, much larger than the space of all control strategies without feedback. So it's very good that we have these powerful methods available to find those feedback strategies. Then the mere fact of being model-free, so that you can treat the model as a black box or even as the real world responding in some way, is very important if you want to apply it to experimental systems, which maybe you have calibrated to some good degree, but possibly not perfectly. And there are issues such as the measurement, that is the observations, which also would need to be calibrated. And so it's very good that the reinforcement learning approach, when applied to that, since it's model-free, can deal with all these complexities and learn them and effectively incorporate them into its own strategy. Then, of course, if we combine reinforcement learning with deep neural networks, we can really handle practically arbitrary observations. These might be images, of course, of video or sequences of measurement values, but you can also invent other formats of the input. If you have an idea that a certain computation applied to the input might present the input in a manner that is better amenable to analysis by the neural network, then just go ahead. You feed it into the neural network and see what happens. So you can pre-process the input at will and see whether the network can make use of that. There are, of course, also challenges. So first of all, you need to see very many evolutions. We are talking about the tens of thousands of evolutions that you need to try out in order to find a meaningfully improved strategy. And also, I mentioned last time, if the optimal strategy is very isolated, so there's many strategies that would give you 0 reward, and only one strategy that is the magic strategy that gives you some reward, that is not something that reinforcement learning is good at finding. Basically, then there is only brute force. Okay. So let's switch to having a few examples of reinforcement learning applied to quantum physics. And before coming to our own research, still a little bit of history or background or context, if you like. This slide just talks about things I've already said. Traditionally, when people were talking about quantum control, they were talking about, say, numerical pulse optimization techniques such as GRAPE, that uses gradient descent in that case. These new machine learning techniques, not only are they model-free, I have said that, and easily can include feedback, but also they profit from all the developments in computer science. So I yesterday talked about these frameworks, these libraries that you can use for reinforcement learning. And that means once you have set up your scenario, you can just fetch the newest approaches from these libraries without having to implement them yourself. So that is very convenient. Here's an example of one of the earlier cases where people applied reinforcement learning to quantum systems. It's still a very simple system. Imagine a spin, and you give sudden pulses to the spin. You can flip the spin around and make it, for example, less sensitive to decoherence, or try to prepare a quantum state in this way. So it's called bang-bang control. And that is something that was analyzed quite intensively in 2018 using table-based Q-learning. And they put particular attention on also analyzing, so to speak, the statistical physics or the statistical behavior of the learning process itself, whether it gets stuck somewhere or not. Here's another very nice example, also from 2018, that deals with producing quantum optical setups, say combinations of beam splitters and mirrors and maybe nonlinear devices, in order to produce, in this case, highly entangled states. And that originally, the whole concept is from Mario Krenn and Anton Zeilinger originally, and this particular reinforcement learning application to that setting was from the group of Hans Briegel in Innsbruck. They were using not any deep reinforcement learning, but their own so-called projective simulation reinforcement learning technique, which has something to do with random walks inside the agent, so to speak, inside the brain of the agent. Okay, so this was the situation around 2018. I talked about the bang-bang control. That's something I mentioned. I talked about discovering optical experiments. There was a very early kind of reinforcement learning applied to the question of adaptive metrology. So you want to figure out a quantum state, what's the best sequence of measurements, and if you want to adapt your measurements to what you have learned so far, how do you do this? So that is from Barry Sanders' group. And then in 2018, basically simultaneously, two works applied deep reinforcement learning to quantum physics for the first time. One was a very nice work by a team led by Moritz August, control of qubits and spin chains, that's yet without feedback. And the other work is the one from our group that I will be talking about that included feedback in order to do something about quantum error correction using deep reinforcement learning. And then several months later, there started a kind of avalanche of different works that continues to this day. Okay, so this is the first work that I want to present to you. What's the setting? Well, the overarching goal is to apply deep reinforcement learning to quantum physics, but then you look around and want to figure out what would be the tasks that are best suited for this. And you realize, well, one of the powerful aspects of reinforcement learning is that it can easily deal with feedback. So having measurements and deciding based on the measurements what to do next. So you look around for a quantum feedback-based challenge in quantum physics. And what comes to mind is quantum error correction. So the setting is you have multiple qubits. They are subject to noise. Noise will lead to decoherence that destroys the quantum information. And the question is, can you keep these qubits or the quantum information alive as long as possible? Initially, this was not even clear whether that's even possible in principle, say at the start of the 90s, and that was a very important potential bottleneck for the whole idea of quantum computation. But then Peter Shor, the same who invented the factorization algorithm, came along and said, no, even though qubit manipulations look a little bit like analog computing, because you can rotate the spin on or the qubit state on the Bloch sphere continuously, even though that is the case, if you're smart, you can come up with an error correction technique, even in quantum systems. And that error correction technique will then involve entangled states of qubits. It will involve smart gates applied to these entangled states, even to produce them at first. And it will involve clever measurements that are chosen such as not to disrupt all the quantum information, because measurement is projective in principle, so you have to be careful. And if we want to place this into the setting of reinforcement learning, we would say that this little piece of a quantum computer, this little module of a few physical qubits, we would call this the reinforcement learning environment. Here it's particularly important to emphasize the reinforcement learning environment, because from the point of view of quantum physics or open quantum systems, of course, the quantum noise acting on the qubits would be the environment for the qubit. So that's something different. Okay. And then the agent, well, that would be kind of the device that tries to control your little quantum module, your few qubits. So it would be able to perform measurements with binary outcomes, 0 or 1. These measurement results would presumably be fed into a neural network to decide what action to take next. And the next action could then, for example, be to apply a quantum gate to one of the qubits, or maybe to perform yet another measurement. I will come to that later. Okay, so to make the situation really clear, we have to define our game. And it starts by saying that you have initialized one of the physical qubits into a arbitrary superposition state. That's the quantum information you want to preserve. So alpha and beta are arbitrary, and the strategy we want to come up with should work for arbitrary alpha and beta, and you should not need to know the superposition state. So it's not about stabilizing a known quantum state, that would be something else, but it's about stabilizing arbitrary quantum states. So now, in order to present what's going on, I'm using the usual quantum circuit language. So time runs to the right. Each of these lines corresponds to one qubit. Here there are 4 physical qubits. And one of these qubits has now already been initialized in this particular superposition state. The others you can think might be initialized, say, in the 0 state. And now whenever I apply an operation, I will place a symbol here. So for example, I could apply a controlled NOT operation, meaning that I will flip the second qubit depending on the state of the first qubit. So depending on the state of this control qubit, I will do something to the second qubit. If the control qubit says 0, nothing happens. If it's 1, then I will flip the state of the second qubit. So that's already one gate applied. I can continue to do this. If I don't know anything else, I might try out random stuff and hope that I stumble onto a good strategy in order to preserve my quantum information. But if I then at some point remember that in addition to applying such qubit gates, I could also very well do a measurement. Let's do that. It turns out that if you have followed very closely the sequence of gates and you know your quantum physics, that this has been a very bad decision. Because what has happened by now is that by these sequence of controlled NOT gates, I've entangled all the qubits. So now instead of having just a superposition of a single qubit, I have a superposition of 2 multi-qubit states. I have something like 0, 0, 0, 0 plus 1, 1, 1, 1, or alpha times 0, 0, 0, 0 plus beta times 1, 1, 1, 1. And now if I measure one of the qubits, even not the initial qubit, that will completely project the full quantum state onto one of the 2 branches of the superposition. So maybe now everything becomes 0, 0, 0, 0. And I completely lose my information of these superposition amplitudes, alpha and beta. So it's completely gone. I stochastically collapse the quantum state. So instead of having helped with preserving the quantum information, I've actually made things much worse. So that's obviously what we want to avoid. And why I showed you this little game is simply because that's the situation that the neural network agent faces. At the beginning, it does not know what's happening. It just knows that it can apply these different actions like C0 and so on. And it just has to try random stuff. And obviously, a lot of the time, it will just end up with something very disappointing. Okay. So the overall goal then will be to discover error correction strategies from scratch without us putting in already some knowledge. And doing so for arbitrary noise and arbitrary hardware constraints. Hardware constraints may mean which qubits are connected. That is, if there are 2 qubits, it's not always a given that you can apply a controlled NOT between those 2 qubits. Maybe they are far away on the chip, so then you have to do something more clever than that. And so to put this into context, of course, we are not in 1994 or so. So it's not that we are still scratching our head whether quantum error correction at all is possible. We already know a little bit about it. And there are actually several approaches. So these approaches I've depicted here in this picture, depending on, say, the temporal correlations of the noise and the spatial correlations of the noise. So temporal correlations might mean either the noise at one instant of time is completely uncorrelated with other instants of time, so something like white noise acting on my system. Spatial correlations, either different qubits experience completely different noise, or maybe they experience even the same fluctuating magnetic field, let's say. So this gives rise to different possibilities for quantum error correction or mitigation. The biggest group of approaches is the so-called stabilizer codes. This is what Peter Shor invented and was developed by many others to produce entangled states and then treat them in the correct way. But there are also simpler, more physically minded techniques, for example, dynamical decoupling, where you apply pulses rapidly on your qubit and then it becomes less sensitive to certain frequencies of the surrounding noise spectrum. You can have decoherence-free subspaces where you make use of the fact that if it's the same noisy field homogeneously acting on all the qubits, then if you prepare certain states, they are less sensitive to that. You can try to estimate your noise and then counteract its effects. And the idea is that if you have a certain hardware platform with some type of noise, it's not so obvious at first which of these approaches is the best, or maybe it's even some hybrid approach if you want to be efficient and efficiently use your hardware platform. And the hope would be that reinforcement learning can automatically discover any of these. Okay. Now there's a catch, obviously. So what I'm going to tell you, on the one hand, it wants to be very powerful in that it wants to work for arbitrary kinds of noise and architecture and so on. And the way we are going to do this is we're going to have or start from at least a rough model of the noise and do simulations on the computer to do our reinforcement learning. Now, these simulations, of course, they act on an exponentially large Hilbert space, or an Hilbert space for the qubits that's growing exponentially with a number n of qubits. So that means automatically we are restricted to relatively small quantum modules, a handful of qubits or something like this. Obviously, we cannot classically simulate a full-scale quantum computer. That would defeat the purpose, and we wouldn't need quantum computing. And so what I'm going to tell you about is really good for optimizing in a hardware-dependent way the performance of small quantum modules. The advantage is then that you are very flexible and your one and the same approach will discover for you the good quantum error correction strategy for different hardwares. This is a reasonable approach because even the experimentalists realize that if you want to have a working quantum computer on a larger scale, then just like in classical machines that become very complex when you go to large scales, what you want to have is a modular approach. So you want to have small modules, those you can test and calibrate and make sure that they work very well, and then you stitch them together. And in the same spirit here, we are thinking of these small quantum modules. Okay, so the way I'm going to structure the story now is I will first give you some results without telling you about the method behind it. And then we will go one step back and I tell you what were the challenges and how we overcame those challenges. But first, just some results to get a feeling of what can be done. So at the moment, we have applied this technique concretely for up to 5 qubits for several different physical scenarios in order to demonstrate how flexible such an approach can be. So here's one example. Here I have just 4 qubits. They are all-to-all connected, that is indicated by these lines. So I can make controlled knots in this case between any 2 of the qubits. And also I can measure any of the qubits if I decide so. Now the type of noise I will assume here in this case is bit flip noise. So with a probability at each time step, any of the qubits may be randomly flipped from 0 to 1 or 1 to 0. So let's see what happens if I apply reinforcement learning to this problem. And as I told you, I will go towards the very precise specification of the method later. But if I apply reinforcement learning, I will observe the following. So here in the upper picture, you see something at the very beginning of training. You see the quantum circuit that results in one episode, in one trajectory, and basically it's random. So you apply, or the neural network agent applies random gates in some sequence. And what happens here is something that I told you about before. Here is a measurement, and the fact that this bluish area stops just means that suddenly the superposition or the entangled state has completely collapsed because of this measurement. So not very good. Okay, so as time goes on, however, it learns to avoid these catastrophic measurements. And as time goes on even further, you see there's a definite pattern to it. So first, there are two controlled knots, which means you produce an entangled state that now involves 3 qubits at the same time. And then there's always a pattern where you have 2 controlled knots and a measurement, and 2 controlled knots and a measurement, and 2 controlled knots and a measurement. And so the experts that have learned a little bit about quantum error correction know what this means. So what it does find is the repetition code encoding. Instead of alpha times 0 plus beta times 1, you now have the qubits encoded in a state of the form alpha times 0, 0, 0 plus beta times 1, 1, 1. The good thing about this is if any of the qubits flips, by comparing it to the other qubits, you can still figure out, aha, this qubit has flipped, I should unflip it. It also discovers parity detection. So what's that? Well, the point is in classical error correction, we can just look at all of the bits and see what the majority say, and then decide this must be the correct value of the bit, even if some of the bits have been flipped. In quantum error correction, we are not allowed to do this, because if we were to measure all the qubits, then of course we would have completely collapsed the quantum state. So what was one of the great insights of Peter Shor initially was that you can do measurements that are good enough to reveal to you where an error has happened, so which qubit has been flipped in this case, but that are not good enough to reveal completely the detailed quantum state. So they will not project you onto one of the 2 pieces of the superposition. And the trick to do this is to ask not the question, what is the state of qubit number 3? That would collapse everything, but just what is the relative state of qubit number 3 and 4? So are they both in the same state, like 0, 0 or 1, 1? Or are they in different states, like 0, 1 or 1, 0? And if you do this on several pairs of qubits, always asking, are they in the same state or are they in different states? You gain enough knowledge in order to figure out whether one of the qubits has been flipped and which one is it. But you do not yet gain enough knowledge to completely collapse the quantum state. So that's the trick. And the reinforcement learning agent automatically discovers that this is the good thing to do, and that it then should apply them periodically. So here's a measure of the training progress. On the vertical axis, I'm plotting some quantity that tells us how good things are. I will come back to that later. Basically, it's how well the quantum information is preserved. And here we see how it evolves during training. So first, of course, it's very, very bad. It doesn't do anything. Then it only finds the encoding. So it figures out how to create out of the initial superposition of a single qubit, the superposition that defines the repetition code. And then it finds out this detection, so this parity detection that I've been talking about. And finally, it goes even one step further. So once an error has been detected, and I'll come to that in a moment, once an error has been detected, it has to figure out exactly what has happened. And there are multiple possibilities possibly, and it has to discriminate between them and see what it has to do. So can we understand what happens in the network? So that was one of the questions we asked ourselves. And that's a typical question. If you have a neural network that performs reasonably well, how do I interpret it? Well, so you want to look at the activations of the neurons, let's say in the last hidden layer, that is a reasonable choice, because the output layer already directly corresponds to some actions, let's say, and the last hidden layer maybe already contains a lot of the structure that is relevant for the problem. But there are 300 neurons in the last hidden layer, so we need a dimensionality rejection technique. And of course, you know how this is done. You use TSME. And what is plotted here now is the following. So we run through these many, many trajectories. And we look at so each point here corresponds to one time point in one of the many trajectories. At this point in time, my little quantum device is in a certain quantum state. So in some sense, each of these points corresponds to that particular quantum state and to what the neural network thinks about this quantum state. And the first thing you spot is there are obviously different clusters. So there are qualitatively different quantum states that the device can be in according to the judgment of the neural network. Now, we want to be a little bit more precise about that. The first thing we can do is we can color things according to the actions that are recommended by the neural network. So this is done here. Obviously, these different clusters then also correspond to different actions. So that's already interesting. But now we also want to know what's the underlying quantum state. You remember the Atari video games. There, the network should propose an action depending on the image on the screen. So you could just plot for each of these points in the TSME map the image on the screen. We want to do the same for the quantum states, but so I have to invent a way to reproduce to present my quantum state. We're dealing with a dissipative quantum system. There's noise, so we don't have pure states. We have to look at a density matrix. And now I have a multi-qubit density matrix, and it may be a little bit hard to interpret it. So what we did was the following. We diagonalized the density matrix and decomposed it into its eigenstates and the corresponding probabilities, that is the eigenvalues of the density matrix. And then it turned out for this relatively simple problem still, the eigenstates had a comparatively simple structure, just superpositions of two multi-qubit states. And now you can try to interpret them by inspecting them very closely. So what you then see suddenly is the following. In these superpositions, say white represents a qubit in state 0, black represents a qubit in state 1. You see something like 0, 1, 1, 1 in a superposition state with 1, 0, 1, 0. So those that are marked in red, they are flipped in the two pieces of the superposition, while the one that is not marked in red, that is just the same in the superposition. And our interpretation is now the following. Aha, this is something like the repetition code, something like 0, 0, 0 plus 1, 1, 1, with slight modifications, but they are not very important. And the other qubit that is left out, so to speak, if we then inspect also the sequences in the quantum circuits, that seems to be the qubit that is used for the measurement, a so-called ancilla qubit, yeah, that I need to have for the parity detection. These are things that we did not prescribe. We just gave the network 4 qubits to play around with, and we initialized one of them with the initial superposition state. But it decided on its own to set aside one of the qubits for this as an ancilla for the parity detection measurements and use the others for the repetition encoding. Okay, and now you can plot these quantum states that look a little bit like the game positions in the AlphaGo. And you can plot these quantum states for the different, for some sequence of states that is visited in a typical trajectory. So you start here, then an action is applied, a gate is applied, you go here and so on. And while you're going through such a cycle, you're also jumping between the different clusters. So each of the states that is observed has a different qualitative meaning from the point of view of the neural network.
Sorry, just a
yes,
question.
Please, yes.
So those clusters that you are plotting, these are basically the activations of your neurons, or
yeah. So the fact that they are clustered depends on what the activations are telling me. So the activations in a certain cluster are very close to each other. Thanks. Mm-hmm. Okay, sure. So When we then look very closely at this particular cycle, we see this is nothing else but what happens when we, when we have this parity detection going on. So we had a measurement, we do a C0, we do a C0, we do a measurement, and so on. So the sequence that I'm looking at is really, so to speak, the standard cycle when nothing particular happens. But once in a while, of course, you will get a measurement result that indicates that something bad has happened. You do not get the expected result. You get something that indicates to you, oh, maybe one of the qubits has been flipped. Yeah, so the parity is not what it's expected to be. In that case, the network switches to a much more complicated sequence where it tries to figure out, oh, wow, which qubit has now been flipped. And you can see this here in the first stages. So initially, there was a quantum state that was predominantly somehow the good, idealized repetition encoding with very small probabilities for several of the other states. But once you do the measurement and get not the expected, but an unexpected result, it collapses onto an incoherent mixture of several possible states that are compatible with this new measurement result. And now you have to discriminate between them, which one is it? Because only if you are sure which one is it, can you correct the error in the right manner. And so it has to go through a much more complicated sequence, also taking into account such things like it may not be one of the storage qubits which have been flipped, but maybe it's the ancilla, which unfortunately during all of this process has been flipped. And so now I'm getting the wrong result and don't understand what's going on. So here, if you look closely enough, you can interpret all these things. Okay. I should remark that the network here really discovers something new. It's not the encoding that is new. I mean, we know, we recognize this as the repetition code that Peter Shor suggested. But even if someone tells you, if the textbook tells you what should be the encoding, that doesn't mean that for a particular hardware platform with particular gates available and particular connectivity, you would know how to go about it. First, to build the entangled state properly and in the most efficient manner, of course, and then how to do the measurements in the most efficient manner, and then what to do, especially if you get this unexpected result and how to go through the sequence. So all of this is automatically taken into account. Now, once you see it works for a more simple case, of course, you can also go to more complicated cases without extra effort on your part. So you just define a different topology. So here, for example, instead of having all of the qubits coupled to all of the other qubits, we just have a linear chain. Of course, that makes things sometimes more complicated because if initially maybe you wanted to somehow, I don't know, swap these outer two qubits of the chain, then if it were all-to-all connected, that would be easy, but here it will become more complicated. Here we have a chain, but we can measure everything instead of only a single qubit. Here we have something even different. And so we can run the reinforcement learning for each of those, look carefully at the sequences, and if we look careful enough, we can see interesting patterns emerging. So for example, here, if you have a chain, it is of course quite well known that one of the most important operations in a chain is to swap, because if you want to couple somehow qubits 3 and 7, you probably need to swap the quantum information through the chain in order to come close to qubit number 7. Now, it depends on your gates that are available. If you say your native gates that are easily implemented in your hardware platform already include the swap, well, that's fine for you. But if it doesn't include the swap, but for example, in this case, a C0, then you have to do something else. And it is known that a combination of these 3 C0s arranged in this manner represents a swap between the 2 neighboring qubits. And so in the course of doing all this quantum error correction discovery on the fly, so to speak, the agent has discovered that, oh yeah, I need a swap, but I don't have a swap, so I need these 3 C0s. Here's another case, but I think so here was a funny case where, since we can measure every qubit, the algorithm for some reason decided it's more efficient actually to not always have the same qubit designated as an ancilla, but to actually swap around the role of the ancilla as it is most convenient at any given time. Okay, so the red boxes are, by the way, the more complicated sequences you get once you have an unexpected measurement result and want to correct the error. And then, of course, you can do quantitative analysis. You can say, well, how does all of this help me to increase my decoherence time? Because that was the whole purpose of the game. So the T effective is the effective decoherence time related to the reduced error rate because of the quantum error correction, divided by the intrinsic physical decoherence time that is short and which you want to fight against. And you see that well, first of all, it's a good large factor, so that's nice, we win. But also it depends on the topology. Obviously, if you have a more powerful topology like all-to-all coupling, the algorithm can discover something that works better than if you have a more restrained topology. Okay. Here's another example, because sometimes I get asked about it. So what about measurement errors? In a real device, given physical measurement only reveals the state to some degree of perfection. And the obvious countermeasure, which is here discovered by the reinforcement learning algorithm, is then to just do the measurements repeatedly. So if you're not sure that a single measurement gives you the correct result, maybe you do it 5 times and then you do a majority vote, and then you can be quite sure what is the result. Okay, so now this all sounded like stabilizer codes. It was stabilizer codes. But the same algorithm also can discover things that have no obvious connection to stabilizer codes. And that's quite important to see. Yeah? So here's a scenario that we explored. Suppose you have 3 qubits, and now there's a fluctuating field. Let's say these are spin qubits, and there's a fluctuating magnetic field. But in a physical realistic scenario, the magnetic field spatial extent is much, much larger than individual qubits. So all of the qubits feel the same magnetic field value at any given time, only during as time progresses, the magnetic field fluctuates. And now let's say one of those is the data qubit that we initialized with a superposition state. And all the other qubits, I can measure them. I may not even be able to entangle them with the data qubit, then maybe I would try something like the stabilizer code again, who knows? But I can measure them. And so, first of all, what now happens is obviously dephasing. The fluctuating magnetic field gives an additional random phase, and the phase then makes a random walk. And so you decohere the superposition state. But what the network realizes is that it can counteract the noisy field by using these ancilla qubits, so to speak, as detectors of the noise. So these ancilla qubits will also, if you think of them as spins, they will precess in the external noisy magnetic field. The precession angle will vary in time. And if you measure them in a clever way, once in a while, you can figure out what's the current value, or roughly the current value of the magnetic field that is fluctuating. And so it doesn't actually do anything to the data qubit. It only tries to measure in suitable time intervals the 2 ancilla qubits. And when we looked closely at what it does, it even found an adaptive measurement strategy. So if you want to find out precisely some random precession angle of a spin, it's not so clear in which basis should you measure. It actually depends on the size of the angle. So what it does is it does a measurement, and depending on the previous measurement results, it then chooses the basis of future measurements in the most optimal way. So again, so to speak, not only does it discover, aha, I want to do this adaptive, I want to do this noise estimation strategy, but also it discovers a good way to do it, namely in an adaptive fashion. Okay, so quick side note, we can use the same hyperparameters for all these tasks. That's also a question one may get. So you don't need to fiddle around with hyperparameters too much between different tasks. There's a good set of hyperparameters where you can learn all these tasks, stabilizer codes, different topologies, different noise sources, and so on, with the same hyperparameters. Okay. So now these were a few impressions of what this can do, but I don't want to give the impression that all of this just works out of the box. You define the scenario, you define the reward, and then you use your library routine, and then it works. It certainly does not do this. So first, what would be the naive approach with which you would start? Well, we have to define a reward. Here, the reward seems relatively obvious at first sight. So you take the overlap of the final quantum state with the initial quantum state, because that's what you want to preserve. Maybe you want to average this over initial states. And maybe you want to take into account that the final state is not actually a pure state necessarily. So, okay, you define the fidelity, but this seems a good start for the reward. Now, we use some policy gradient type technique. So we would define a policy network where the input is some measurement that you have done, some measurement results that you have obtained. And the output, as we have learned in the lectures, would be the different action probabilities. So whether you will do a bit flip or a controlled knot or a measurement on one of the qubits. So each of these, of course, there are multiple versions of them depending on which qubits you are addressing. So in total, maybe you have 10 or 20 different actions that you can take. Now, if you apply this out of the box, it just doesn't work. It just gets stuck. It always does these random sequences. And so what are the challenges? So problem number one, it's a general problem, of course, is just the sheer combinatorial explosion of strategies. And the problem here is a little bit that the shortest useful gate sequences are already relatively long. Yeah. If you only restrict yourself to 2 or 3 gates, you cannot do something really good with those. And to find good gate sequences among these many is really a challenge. So that's the first challenge. And the second challenge is a little bit related. So there are local optima. What I'm plotting here is not the return, but the negative return, so as to make it look that the minima are the good points where you want to be. Now, the most simple strategy you can have is obviously to do nothing. Yeah? You do nothing, just the physical qubit sits there and it slowly decays. We want to be better, and indeed we can be better. There are very smart and complex strategies. You've seen this. But between those complex strategies and the idle strategy is, so to speak, a barrier of incomplete strategies where you have only a few gates of the good strategy, but they will make things even worse. And so it's really difficult to go from here to there. Okay. So we had to come up with some smart ideas. And this is where also some domain knowledge can come in. So of course, the best hope is that you need not even be a domain expert and you just apply you're just a computer scientist. Someone tells you the scenario, you apply out of the box your algorithm, and then everything works and you go home. But often it is that you can make use of some domain knowledge. And that is fair as long as the domain knowledge is still sufficiently general. Of course, I don't want to put in very specific knowledge of this very particular hardware configuration of the qubits, because then I'm solving the problem and not the computer. But if it's relatively general, domain knowledge is still okay. And so here we had 2 ideas. First, to put in as much information as possible, and then to construct a better reward function. And these are quite general still. So when you are facing another reinforcement learning challenge, which doesn't work so easily, you may also consider, what's the information I supply to the agent? Maybe I can pre-process something, maybe I can do something better. And also what's the reward I'm giving? Maybe I can modify it in a smart way. Okay, so first about the information. In the most naive approach, you would only supply to the agent the measurement results. But these measurement results, they are very sparse information. Because first of all, in such a typical quantum error correction scenario, you don't even always measure. Much of the time, you just apply some gates, so then there's no information. And then when you measure, you only measure a single qubit and you just get a binary result, so 0 or 1. So it's very, very sparse information. In principle, it should be enough, and we will see later it is enough, but it's very hard for the agent to start to learn something based on this little information. So I want to compare this with a robot that is blindfolded, yeah? And only very rarely is being told, oh yes, now you're close to a box, and all the other time it doesn't see anything. That is not so good. It's much better, of course, if there's a map. Even then it can still be challenging, because if there's walls, then you still have to figure out what's the best way around these walls. So let's give the agent as much information as possible. Now, what is the most complete information you can give me about a quantum system? Well, that would be the complete quantum state of all the qubits in your multi-qubit system. So if it's a dissipative system, that would be rho, density matrix of all these qubits. And now the alarm bell should go off and you say, wait, isn't this cheating? So for two reasons. So first, in an experiment, we cannot do this, yeah? I cannot stop my quantum computer and then do full quantum state tomography, running it several times until this point, and then see what is the density matrix in order to supply my agent with this information. So that's not possible, obviously. And also, since our task was to preserve an unknown quantum state, once we tell the agent what is the quantum state, isn't that cheating? Because now it knows the quantum state. It could just let it decay and then at the end of time just rebuild the quantum state from scratch. But that is not really what we mean by quantum error correction. Yeah, we have to be agnostic. We cannot see the quantum state. Okay, so to solve the second problem, that the agent should not be able to cheat us, it should not know what is the quantum state and then let it decay and recreate it later. We take into account that what we really want to do is we want to preserve an arbitrary quantum state. So the agent should come up with a sequence of actions that are independent of the underlying quantum state, of the underlying superposition, and should always work. So what we want to consider then instead of the density matrix is even something more general, namely it's what is called the completely positive map that maps the initial quantum state to the quantum state at time t. So it's, so to speak, on the level of wave functions, it would be not talking about the evolution of psi of t of the pure state, but instead the evolution of the unitary operator u of t. And here, instead of the evolution of rho of t, I talk about the evolution of this phi, the map that tells me about the time evolution. So in a sense, I'm treating simultaneously in parallel the evolution of all possible initial superposition states. It turns out this is not so difficult here. If I constrain myself to having only one physical qubit in a superposition state, it is enough to actually time evolve. The numerical effort is the one that I have if I time evolve 4 different density matrices, so it's doable. But what we will ask the network now to do is to preserve an arbitrary state using the same gate sequence. So it's never being told the quantum state rho itself, it's only being told what is the phi so far that would map any initial state to any final state. And so it cannot cheat. So that was one important step here. Now, so therefore we have our network that is really powerful, that is being given the quantum state, or as I just told you, actually something more complete, namely this positive map as input, and then has to decide on the actions. We call this the state-aware network. Okay, fine. And this is the network for which I have shown you the results, which really then discovers these good quantum error correction strategies. So I'm doing a simulation on the computer, I'm evolving this completely positive map, I'm feeding it into the agent at every given time, and then it decides on the next action. That's the idea. Now, this still doesn't answer my other objection about cheating, because this still isn't possible in an experiment, obviously.
I will also just use the moment for the question, just because I lost you for a second. So now you do put in the full density matrix or not? You do something else, right?
Yeah, we do something else. We put in this completely positive map, which can be represented as 4 density matrices, if you like. Yeah. And so that's good enough. So what this means effectively is the following. The agent does not need to learn internally how to evolve quantum states. It does not need to learn the master equation, so to speak. We provide this because we're doing it anyway. But we are doing it in such a way that it will not, even if I gave memory to this agent, it would not be able to just say, oh, yes, now I'm looking at this particular quantum state rho. So let me remember this, let it decay, let me recreate it later. This would not be possible because it has to produce actions based on this completely positive map. So it's not yet revealed which initial state I will use in the end. Okay, so I hope this.
Completely positive map is something that's going to act upon the density matrix. Right?
That's right. So exactly.
That's going to encode your.
So when I talk about the completely positive map, I need not yet decide which initial state I will be talking about in the end.
So that's going to encode basically your decoherence, right?
Somehow. It decodes the decoherence and everything that the gates have been doing so
But then
far.
how do you experimentally know your completely positive?
Yeah. So this I do not know. So that's why I now come to the second step. Thank you. Okay. So this is powerful enough to work well to discover good strategies on the computer using my simulation where I do have access to the completely positive map. But obviously in an experiment it's completely hopeless. So what we have access to in the experiment would be really only measurement results because we do not just want to do things on average, but for a concrete trajectory. And so what we came up with then was something that we like to call two-stage learning. So first we do reinforcement learning for this relatively powerful state-aware network. It's powerful in the sense that it's given a lot of information. And then once we have this and we know these strategies, then we start looking at another network. This other network is really of the type that would work in an experiment. So the input here is really only the measurements. And in order to be able to process them in the right way, it also needs some memory. So this is actually a recurrent neural network, an LSTM network. So this is a network of the type that conceptually would work in an experiment. The question is only how to have it learn the correct strategies. So what we do here is not apply reinforcement learning to this network. That wouldn't work. But since we already have the powerful trained network available, we use it as a teacher in a supervised learning path in order to teach the second network. So the task of the second network will then be to imitate its teacher. Given these measurement results that I'm seeing, I should be able to predict the action that also my teacher, my powerful teacher, would do in this case, even though the teacher, of course, knows much more than I do because it has access to this completely positive map. So this is a general technique that you could apply in situations where the actual application has very limited information, like a robot seeing only the small surroundings in the labyrinth. But somehow you have a simulation available for the more complete situation where you have access to the full state of the environment. Then you do reinforcement learning there. And then you try to do supervised training to teach the good strategy to this less powerful network that has access to less state information. Yes?
Sorry, I bother you a lot, but that just means that you're presenting in a nice way so we can follow. Could that work also to generalize your strategy to a larger number of qubits, which is, for example, larger than you can simulate? But for example, you would train the first network on a smaller number and then use it as a teacher for the second network on a larger number of qubits.
At the moment, I don't see how I would do that, because then of course also the action space changes. It's very hard to see how that would work. Even if I imagine I have a situation which is kind of translationally invariant, you know, I have a chain with periodic boundary conditions and then I make it longer and so on. So I can imagine, at least I can use convolutional networks and so on. But still I fear that I'm not doing something intensive where I just say, oh, first I have one physical qubit. I want to encode it into overall three qubits to form a logical qubit. And then I have 10 physical qubits and I want to encode them, each of them in 3. That would be something that I could see that could possibly scale. Basically, you do the same thing for each unit of 3 now in a bigger system. But at least here, the idea would hopefully then be to say, I still have one logical qubit, but now I have more physical qubits available and I want to distribute them over more physical qubits. And there I don't quite see how to set up the situation so that I can easily extend it. Of course, that is one of the challenges. Yeah. So if one can come up with a good idea to transfer it to a larger number of qubits in this non-trivial fashion, that would be very helpful. Mm-hmm. Okay, so back to two-stage learning. Powerful network trained with reinforcement learning on simulations. A network that has much less information available, trained by supervised learning. And then you can deploy this in the experiment. That's the idea. And here's the outcome of the supervised training. So that's the teacher talking to the student. We have here 2 measures of the quality, so to speak. There's recoverable quantum information that I already showed you, and the simple overlap between initial and final state as they evolve during the supervised training of this secondary network, and it becomes better and better. So that's good, but it works really nicely. What is even more exciting, I find, is to analyze the workings of this recurrent network. Yeah? So this is a network that has memory. And what I'm plotting here is different neurons of this network as a function of time and their activation, say, as a density. And as time progresses, of course, I'm also applying all my gates. That's the trajectory that I'm looking at. And in the middle of the sequence here, indicated by this red box, some unexpected measurement has occurred. So then suddenly the sequence has to switch and it has to figure out which qubit is wrong and which qubit should I correct for. And what you can identify by very closely looking at these neuron activations is, well, there are some counters, obviously. So neurons that somehow go like 1, 2, 3, 4, 1, 2, 3, 4. So during the normal detection cycles, they count, so to speak, which step am I in currently? Yeah? And then apparently there are also neurons that switch completely once you are in this new mode, so to speak, when you're trying to do the error correction sequence. More than that is a little bit hard to tell because, as usual, looking at neural network activations, if you were to retrain the same neural network, of course, they would look somewhat different. That's the usual thing. But it's already interesting to see that there's such a correlation between what happens in the actual trajectory in the quantum circuit and what happens in these memory neurons. Okay. Good. So finally, the smart reward scheme. So this was about taking into account more information in a way that it's not cheating and that we can still apply it to the experiment. And the second part is, can we improve our reward scheme? So the naive reward would just be to say, what's the overlap, the final overlap between the final state and the initial state? No? Okay, good. But that's only decided at the very end. And so that's a problem because as I'm still searching for the optimal strategy, I'm doing maybe a few things right at the beginning, but then a lot of things wrong and the quantum state collapses. And then when I measure the overlap at the very end, it's just 0, so to speak. Yeah? And then I do something again, and it's still 0. So I basically get no learning signal. I always get 0, 0, 0, you're bad, bad, bad. And then the agent doesn't even try anymore. So it would be much better to have something that guides it a little bit towards the good solution, even if it's not yet perfect. And so in the game of the little robot, that would mean that even if it's not yet on a box, it already smells the box in the vicinity, so to speak. A little bit like the value function or so. But the question is whether we can build a reward scheme without putting in too much knowledge, of course. I can always, if I know the correct strategy, I can always build a reward scheme with instantaneous rewards that basically amounts to supervised training, but that I do not want to do, obviously. Okay. So the idea we came up with was the following. It would be good if at any given intermediate time, you could ask yourself, how much of the quantum information that was initially there is still there? The problem with this is that the quantum information by now has been distributed, because the good quantum error correction strategies often involve entanglement. So the original physical qubit where the superposition resided now has been distributed, so to speak. It has been entangled with many other qubits. So you have a very complicated entangled multi-qubit state that somehow still has the initial quantum information, the alpha and beta of the superposition available, but it's a little bit hard to disentangle, so to speak. Yeah? And in principle, what you want to know is, if I now were to stop my game, my quantum circuit, my evolution, and then do some decoding to try to bring back everything into one physical qubit, then what would be the overlap with the initial state, right? If you could answer this question, that would be good. Unfortunately, it would also be very hard to find this decoding scheme, so we are stuck a little bit. Yeah. So anyway, it would be good to have such a measure in order to treat situations such as this, where say here is a bad measurement that collapses everything. Previously, apparently the amount of quantum information, however we define it in the end, was large. And after this collapsing measurement, it's really bad. And so the idea we came up with is the following. We start, say, with a superposition state. And it evolves into a very complicated entangled state. But if there is no noise, then obviously it remains a pure state. And so what this means also is that if I have initially orthogonal states as represented by these two Bloch vectors pointing in opposite directions on the Bloch sphere, then these initially orthogonal states in a completely pure ideal evolution would remain orthogonal. Yeah? And if I don't have an ideal situation, the problem is that they become ever closer. And for example, if everything decays to the ground state, then regardless of the initial state, I'm ending up in the ground state and I cannot distinguish them anymore. So the question is, if I have two initially orthogonal states, how much can I still distinguish them after some while? That teaches me something about the quantum information that is still there. And so people know how, in principle, how to answer such a question. So if I have two quantum states represented by density matrices, what's the probability to distinguish them if I were to carry out an optimal measurement? This doesn't yet even reveal to you what is exactly the optimal measurement, but this quantity teaches you what would be the probability to distinguish by an optimal measurement. And so what this led us to was to define what we call the recoverable quantum information. So at any moment in time, you ask yourself, if I started out with two initially orthogonal states, what is the distinguishability, so to speak? And you even minimize over the initial state. So maybe different initial states decay more or less fast. So you want to take the worst case. And that is our measure that we are optimizing for, and which works very well, actually. So now I'm looking at the clock. I think this would be a good place to stop here. I still have a few slides to finish this example, and then there's the other example, but maybe there are still some questions right now.
Yes, so do we have some questions, please?
Hi. I was wondering, in this double learning scheme, where you go from the positive map to then just teaching a network that takes the measurements and acts as the previous one. Could that mean that, for instance, you could predict? Okay, so it means that this measurement information is somehow sufficient to choose the proper action. So could that mean that from this measurement information, you could infer the positive map?
Yeah, so this measurement information has to be sufficient. So because what's going on is the following. The agent, of course, knows what actions it does. That's actually also part of the input I should have specified, but that's normal in reinforcement learning. So the agent knows what gates it applies. And as long as there is no measurement going on, that is sufficient to also then, in principle, calculate by just evolving the master equation, the completely positive map. And then once there's a measurement, of course, then there's a concrete binary classical decision. And then it needs to be told what was this decision. But by knowing all the previous measurement results and knowing all the gates it did, you can construct a completely positive map.
Okay, because then the state is not actually just the measurement results, but also it keeps track of all the gates it's placed.
Yes, so I should have said this. So this is the current measurement result, and there would be an additional input neurons, say, that specifies the last gate. That's important, of course. That's always true if I do, well, it depends a little bit on the situation, but in the most general situation, if I do policy gradient, since the action choices are stochastic, the agent needs to be told what was the last stochastically chosen action concretely, if that is important for the further strategy.
Yeah, okay. And I guess that the long-term memory is encoded in the LSTM, basically.
Yes, yeah. So this is depicted here by these little circular arrows.
All right. Perfect. Thank you.
Mm-hmm. Here, yeah.
So coming back to previous questions, this two-stage learning cannot yet be applied to experimental platforms, right? And so since the publication of the paper, have there been proposals to...
What do you mean cannot yet? So you mean it has not yet been applied, or what?
So you could not find the perfect error correction schemes for large platforms. You have to train on a smaller system numerically.
Yes, that is certainly true. Yes, that has nothing to do with two-stage learning. It's just a limitation of having to, at some stage, simulate the workings of this quantum memory. It would be, say, if this approach would work out of the box without going through this stage, then you could imagine, in principle, directly training on a quantum device. Of course, you have to supplement this at the end by some measurement that will teach you something about the fidelity, but this can be done. So if neither this added information nor this improved reward scheme were needed, and this challenge would be simple enough to work out of the box, so to speak, then one could, in principle, conceive directly training on a quantum device. Even then, of course, whether that scales rapidly to larger numbers of qubits is still open, because even though you might say, okay, but then the quantum device simulates itself, so that part is taken care of, still the complexity of the strategies, of course, also improves, also increases, and that may still be a bottleneck.
So this is not the case. You still need this, the left part of the diagram.
Yes, so I need the left part.
Yes.
And then in order to apply it to the experiment, I do supervised training on the second part, and this is the agent that is applied to the experiment.
Yeah, so I was just curious, are there any other reinforcement learning schemes that are more scalable, maybe, been proposed?
Well, so the only thing I'm aware of is when people start from something where they take already many ingredients as granted, like, oh, I have this surface code, I know its scheme, And I want to use reinforcement learning only for particular components of the surface code. And then, of course, you can think of larger qubit systems.
Okay, thanks.
I have a question. Is it possible after you train this student neural network to actually like basically retrain it with actually quantum data like afterwards, like basically like fine tune it?
Yeah, so that is in principle possible. How well it works would have to be seen. So what we observe is, of course, the following. For a long time, since these are discrete actions, for a long time, if you change the parameters of the noise and so on, the strategy may remain the same until it suddenly switches to a different strategy. So then the question is, what is the case in your experiment? Say you calibrated it reasonably well, you put this model here on the computer, you used reinforcement learning to find a good strategy. Now you try to run it on the device and it works, but not yet quite optimally. Yeah. And so then you start to further fine tune it in this way. So that could conceivably be done. But the challenge is a little bit if the fine tuning, well, if the experiment is relatively close to the situation that you simulated, then probably the strategy won't change anyway. If it is significantly different, then maybe you would have to switch to a completely different strategy, which I fear would mean almost starting from scratch. And then I think it will not work very well.
They might actually get stuck in this local minima.
And actually get stuck.
Okay. Thank you.
Any more question? If not, then I think we'll take 10 minutes break. So we are back at 51 past 12, and then we'll have like the last 40 minutes. Okay, so I think now we will have the last part of the last lecture of the school.
Okay, thank you. So just to recap, we talked about using reinforcement learning to discover from scratch quantum error correction strategies based on feedback. Now, in the future, first of all, you could apply this to other physical settings where maybe you don't just have qubits, but also have cavities with correspondingly different controls. Or maybe you have ion traps where you know they have these ideas of ion chips where you can shuffle around ions, and then some of the actions that you perform may not be quantum gates, but actually this shuffling around, which changes the connectivity of the qubits de facto. There's a couple of things that you can try to improve the physics simulation, the acceleration of the simulation. Other RL algorithms we already tried, just didn't publish so far. Monte Carlo tree search, we tried and failed in the first attempt, but okay, we'll see. What we are currently most interested in is obviously implementation in experiments. That will not be directly the full quantum error correction stuff, but we are working together with people in Zurich to make this happen. And then you really want to have the neural network be implemented, so to speak, on the chip so that it can quickly react to the measurement results. The measurement takes place in 100, 200 nanoseconds, and that's also typical, say, gate times for 2-qubit gates or what. And you need a network to compute the next action on this time scale for it to be useful. And so there are many tricky technical challenges to make this happen, but we're on it. Okay. So now I want to switch to another case study of where we have used reinforcement learning, and that is for optimization of full quantum circuits. So now we will be talking many, many more qubits, but the setting is also different. And that was work done with colleagues at Google Research. Okay. So here's a quantum circuit of the type you've seen before, only a little bit larger, with several gates being applied. And the question is, how can you optimize this? So this particular quantum circuit implements some algorithm, but on the physical level, it just represents one big unitary, one big multi-qubit unitary. And the question is, maybe we can delete some of these gates or turn them into other gates in such a way that the total unitary we have is still the same. So it's an equivalent circuit, but maybe it's shorter or has less gates. And that is particularly important right now, where we have these noisy quantum devices that are already kind of large, 50 qubits, maybe 100 qubits, but that are not yet as big as to easily allow for abstract high-level logical qubit quantum error correction. So in this case, we want to optimize our circuits in order to counter the noise, counter the effects of the noise. And this circuit optimization really needs to be hardware dependent, depending on which gates you have available. Now, how would this work in more detail? We know there are certain transformation rules where maybe you move one gate from the left of another gate to the right of another gate, and you see, oh, this actually doesn't change anything, because if I rotate around the z-axis, the control qubit of a C0 gate, I can do that before or after. That's fine, it's the same. You can say, take these two C0s and expand it into a larger sequence of C0s, or go the other way around, which is maybe more appropriate here, and so on. So there's a handful of transformation rules, and we do not supposed to find these transformation rules on the computer. So these you can enumerate by hand, depends on the gate set you have available. But we want to apply these transformation rules to a given quantum circuit, and we want a computer to learn to apply them in an efficient manner. So here's the setting then. You would have the original circuit, and you hope to come up with an equivalent but more efficient circuit, shorter time, smaller gate count. And you want to do this by reinforcement learning. And so in a nutshell, as an overview, what should happen is that you view this whole quantum circuit at once, like the board game, the board of a game. You view this whole quantum circuit, you have to represent it somehow, feed it into an agent, and the agent has to decide, where do I apply one of these transformations and how do I apply it? And so once you can do this, you have arrived at an approach that is then fairly autonomous. You still have to supply a few transformation rules, but that's it. And is hardware efficient in the sense you really take into account the details of the particular hardware platform. You could also put in things like some gates maybe are considered more expensive in the sense they take more time, or the decoherence rate is larger, which we didn't do right now, but this all could be put in. Okay, so how would this work in practice? So first of all, we have to feed in the quantum circuit. So we have to encode it in a proper manner. And so what we opted for was kind of three-dimensional representation. So the quantum circuit itself already looks two-dimensional. So there's a moment in time and the qubit number. But then at each moment in time and qubit number, you can have one of several different gates that act on this particular qubit or on this qubit and its neighboring qubit. And so the way we want to look at this is we want to say, this is like an image input for a convolutional network, where the two-axis qubit index and moment are really two spatial axes, so to speak. And this third axis, the gate class, that's more like the different channels, the different color channels of an image. It always depends on where you have translational invariance and where you have locality. Wherever you have translational invariance and locality, these should be the spatial axis in a convolutional setting. But any other information that should count as a channel. Okay, so that's the observation. So if in particular you have a particular C0 at this location, then there will be a 1 at this spot, and otherwise you have 0. So it's a one-hot encoding in this sense. Okay, and now you feed it through a convolutional network pipeline. So that's in the middle here. And then afterwards, you produce an output, and I will discuss it a bit more in detail in a moment. But the technique we use is one of these advantage actor critic techniques. So we will calculate both the policy probabilities for the different actions, as well as the state value. And so that's what's shown here. The output for the policy is a suggestion to apply one of these transformation rules at a particular spot in the circuit. So again, it's a three-dimensional object. Two of the axes are again the time and qubit number. And the third axis would be the transformation rule that you want to apply at this particular spot. And now the entries of this greenish 3D object are just the probabilities of doing these different actions. It's very close to what happened in this AlphaGo, where you have probabilities on this two-dimensional board. Now you have probabilities on this three-dimensional grid. And then the state value, that's another single number, so to speak, that you get that tells you how good is the current quantum circuit, how well am I doing at the moment. Okay, and so taking all of this together, I still have to tell you what is the reward. Well, that would be the reduction in gate count, or the reduction in depth, that is the time needed overall, or maybe a combination of both. In the end, in any optimization problem, of course, you can only optimize one number. So that's what we can put in. And as I said before, in principle, we could also put in something like a decoherence estimate. We look at the gates and we say, oh, this gate has a certain decoherence rate. And then we calculate the overall decoherence rate or an approximation to it that we expect. Okay, so now for the training, how do you train this actually? So the bottleneck here is a little bit that it's not so easy to produce a lot of quantum algorithms, so to speak, to train on this compactification that we want to do here. And so what we did is we implemented random circuits. So let me walk you through how this works. At first, we just produce random gate combinations that produces a quantum circuit like the one shown here, with a certain gate count, with a certain depth. This random quantum circuit will have some obvious simplifications that you could try to do. We call it pruning. So that reduces the gate count and so on. And that forms a kind of reference circuit. It may not yet be the optimal circuit, but it's a kind of reference that we have. But if we were to start from there, and if we wanted to train our agent starting from there, this is already a relatively compact circuit. And then at least in the beginning, when it's not yet good, it would not really discover much that it can do. So what we then do is something dramatic. We just apply random transformations. And that typically these random transformations, if you really pick them at random, will not really shrink the circuit, they will expand the circuit. So in the end, you end up with such a gigantic random circuit that is really inefficient, so to speak. And then we let our agent run. The agent is given the circuit. Since the circuit is so inefficient, even a bad agent is able to discover a little bit of a strategy. And then it shrinks the circuit. And if it's already well trained, it will shrink it hopefully to even a smaller, more compact size than this reference circuit that we got after the initial stage when we pruned and threw out and applied the most obvious simplifications. Okay, so that's the training that we do. Random circuits that are inefficient, our agent tries to compactify them. And here you see what's going on. So the depth and the gate count as a function of training progress, they go down, of course, as they should. And then you can also look what happens in a particular optimization attempt. So for a particular circuit, you start and you try to, the agent tries to optimize it. And so these are these orange curves as it applies the transformation rules in the manner that it has learned. It has now learned to spot the good opportunities, where to apply them, the depth and the gate count, what we care about, go down. You also see it's not yet completely perfect. Sometimes there are glitches where it applies a transformation rule that temporarily gives it a larger gate count, but that's fine. Okay, so now we wanted to compare the performance, but it's a little bit difficult because what do you compare against? And what we ended up comparing with is a general optimization technique that works reasonably well for discrete settings, that is simulated annealing, where you apply, you pick random transformations and try to see what happens if I do apply this transformation. If the gate count is reduced, you keep it. If the gate count is not reduced, but rather increased, you keep it only stochastically. And that is something like, well, thermalization at a given temperature. If you prefer the optimization, the improvements more and more, that means you have a lower temperature. So that's simulated annealing. And when we compare this, we find the following. So simulated annealing always takes the same time per circuit. And for the circuits shown here, that was counted in days, actually, because it uses quite a lot of rounds of trying to feel its way towards the optimal solution. Reinforcement learning works differently. Here we first have the training phase, and that really took a week here for these parameters and so on. So taking a week to find a strategy, but then you have an agent that really works for any given circuit. You throw any given random circuit at it, it knows what to do automatically. And then it's quite efficient. It only needs 2 minutes per circuit. Yeah, so the simulated annealing starts always fresh. It doesn't know anything. It needs a day or so. Reinforcement learning after it has been trained, 2 minutes. Now this would mean, of course, you can calculate for yourself if you want to apply it, for how many circuits you want to apply it in order for this to pay off. But things become even better if you go towards larger number of qubits. And that's now possible because this agent uses convolutional networks. So automatically it uses locality and translational invariance, and it can immediately be applied to larger numbers of qubits. So that's a little bit a case of transfer learning that works. Again, for these larger qubit numbers that go into the regime that is experimentally relevant, for these 50 qubits, for example, simulated annealing would take 1 week to optimize such a circuit. And that's comparable already to the full training time for a general reinforcement learning agent, which then can be applied to arbitrary such circuits and only needs a few hours to run on any given individual circuit. Okay. But finally, we also wanted to test it by applying it to a kind of real quantum algorithm. The example we took was quantum approximate optimization, specifically for the max-cut problem. So max-cut problem is essentially if I give you an arbitrary graph and put the Ising model on this graph, the antiferromagnetic Ising model, then find the ground state. Okay. And it may be a little bit hard to find this ground state of lowest energy because there is some frustration involved and so on. And you can phrase arbitrary optimization problems in this way. And so there's a known algorithm how to find a way towards better solutions for the ground state of this setting. So you translate a graph on which you want to work. You translate this into quantum gates. And this is still more abstract, the logical circuit. And this is, so to speak, the compiled circuit with concrete C0 gates and so on. And then you string them together. All of the, there are gates that are parameter dependent. And the idea is then, like in a variational approach, you vary these parameters and to test how good is your solution.
Sorry, a question.
Yes, please. Yes.
There are these theoretical results for what are the optimal gate counts for like circuits of given size. Of course, they only exist for like small circuits. But just out of curiosity, how do the gate counts that the neural network finds compare to those optimal?
Okay, that we did not compare. Yeah, that would be maybe a good thing. I wouldn't know how to do this for these actual large-scale circuits.
Yeah, no, I think the theoretical results are only for 3 or 4 qubits, and then they give some.
But it would still no. But it's a good point. Yeah, maybe one should do this. It should. At least I mean, in the end, it should find these optimal solutions. Obviously. I will say a little bit more in this direction a little bit later. So there's a difference between the, so to speak, meta agent that has been trained on arbitrary random circuits and then can try on site to optimize for any given circuit. There's a difference between that and when you do reinforcement learning for a specific circuit, which you can also do. So you keep the circuit always the same and you say, oh, now I want to do reinforcement learning for this. That can still give you a little bit, a few gate counts less. And so maybe it would be good to compare also this.
Because I know at least from a couple of years ago, there was a lower bound, but it was known that it was not optimal. So maybe you beat that and it could be an interesting result if you beat the kind of lower bound.
Well, thank you for that suggestion. Okay, so let's take this as our quantum algorithm and we have a compiled circuit. Before optimization, it looks like this. So it consists of many blocks which have been hand engineered, so to speak, and you stitch them together. And now when the agent performs on the circuit and tries to compactify it, it at least improves by 10%. Now 10% may not feel that much, but you have to realize that these individual blocks, of course, were already engineered by hand to be optimal. And so where the agent then sees some optimization potential is always at the interface between the different blocks. And then just what I mentioned before, instead of taking this general agent that was trained on completely arbitrary circuits and apply it to this particular circuit, you can also train an agent only for this circuit using reinforcement learning. And then it gets a little bit better. And you can then analyze where it gets better. And these were transformations where it had to go through many steps that first blow up the circuit and then get smaller again. And then it gets a little extra reward. So it's quite difficult to find these extra optimizations. Okay, so then let me wrap this up. In the future, so this is already nice. In the future, of course, we would imagine that you take, okay, there are databases online, of course, of different algorithms. There are also compilers for quantum circuits that say depend on the gate set you have available. And then if you can produce a sufficiently large quantum circuit data set for the purposes of this compactification, so to speak, then you could train on that. And then it would be very interesting to see whether by training on that, you discover extra modifications of the strategy as compared to the random circuitry. Good. So that brings me to the end of my lectures. There's still time for questions. That's good. So we learned everything about reinforcement learning, a little robot wandering around the world, moving around objects, trying to get a good reward by solving some task. We now also learned that this can also be done if the robot interacts with a quantum world, superposition and entanglement. One thing that I did not talk about is, I just briefly mentioned that if you want to model not only solving particular tasks, but so to speak, making an artificial scientist, an agent that can discover things, that decides, oh, what's the hypothesis I should put out? What's the next experiment I should do in order to refute this hypothesis possibly? Then if you think of this general setting, general artificial scientific discovery, then also reinforcement learning is probably the way to go eventually. Okay, and so little advertisement at the end. So our group is obviously interested in applying deep learning to quantum technologies, but also in this process of artificial scientific discovery more generally that I just mentioned. And there's typically some postdoc or PhD positions available, so you can send me a mail if you are interested in that. And then before I'm completely done, and before I take questions, I want to take this opportunity to thank the organizers for putting together this wonderful summer school under really complicated circumstances. So I think the organizers deserve some applause.
Thank you very much. So now time for questions. Yes, and I regret that I'm not looking for a PhD position, but yes, please.
Okay. So, any questions about robots and environments?
So one question for the last plot that you are showing with the optimization of the circuits. Yes, this one. So I was wondering here if you could comment a bit also on the, so this is like the best optimization that you found with this reinforcement learning.
Yes.
But could you also comment a bit on the variance of how well it performed? No? Because here what we see is that between the model that is trained on a random circuit and on a specialized circuit, I mean, the difference is not so huge. But is it like within error bars, or what would be the error for the?
I'm trying to interpret this. So maybe with variance, one could be referring to graphs such as this, where I'm applying the agent to some given circuit. And then as it settles into close to the optimum, there are still these glitches. So if I were to stop, so to speak, at the wrong point in time, I would not be quite optimal. But I fear we haven't analyzed this very much further. You see these glitches are always on the order of ±1, so to speak. It also gets still a little bit better if I train further, then it becomes more certain of what it should do and that it should now stop. So that would be one kind of variance, so to speak, for a given circuit, how it fluctuates temporally when I'm going through my transformations. I could also ask another type of variance. I could do the reinforcement learning from scratch several times, so to speak, get agents that have been trained for the same amount of time, see how they whether they disagree on a given circuit. I fear we haven't tested this. Maybe we should, but that's a good question.
Definitely.
Right. So I have a question, maybe it's more technical regarding the architecture of the agent, because okay, let me think for a second. Because here, so the idea is that the circuit is some sort of the image and the gates are a channel.
Yeah.
And I was wondering, in order to perform the transfer learning to larger circuits, all right, you don't need global pooling, right? Because you need the output.
Well, for the state value, there is some global sum you see here, but that's fine because that is also translationally invariant, so to speak, that's fine. And for the rest, there is actually no flattening or pooling or so going on. It's just, it just scales up.
Yeah, I see. And then I was wondering because I guess you always take the C nodes that only act on 2 qubits that are neighboring.
Yeah.
Right. And then what would be the kernel size that you're using? Like how farther up or on the sides?
Okay, so that question, unfortunately, I cannot answer right off the top of my head. So the kernel sizes you mean that we used here for the I don't think that we used anything crazy like 3 or 5 pixels or so. I mean, if you have enough layers, that if you want to spot the opportunity for a transformation rule, it's typically the local environment of a few surrounding gates that should matter. It should not. You don't need so many layers or a large kernel size that you can have really long range correlations that would be quite difficult to learn anyway.
Yeah, that's why I was wondering whether the strategy would be like to take, I don't know, 3 or tops 5 or something like that, or well, I don't know. Yeah, it's perfect. Thank you.
Okay. But since you mentioned the C nodes only connecting neighboring sites, that's of course that could be a little bit a bottleneck if I now were to take more complicated geometries. I mean, I could obviously take a 2D grid and then just have also local C nodes to neighboring sites, no problem. But if I had a more complicated graph, then I would need to think again of how to represent the circuit, obviously, and also how to represent the different transformation rules, because then if I can have a C naught between qubits 3 and 17, because that just so happens in this graph, it will become more complicated.
Yeah, okay. Yeah, it was one of my main concerns regarding these convolutional things, because since these are only into neighboring qubits in the representation graph, it's nice for convolutions, but I was wondering what would happen with what you mentioned. No?
So in principle, of course, there are these graph networks that can take as input a graph. We haven't tried them out here. This would be another technical development, but so far not.
Yeah, very nice. Thank you.
Okay, one more question. So when the agent actually optimizes the circuit, you just randomly sample from the policy and then apply it, or?
Yes. Yeah.
Okay. So could you also do some like policy-based Monte Carlo tree search like they did in AlphaGo?
I suppose yes.
because I think especially if it gets stuck in the end, then you might need like a certain sequence of moves to get you out, and if you do like a Monte Carlo sampling, that could actually help.
I completely agree. I mean, this has a lot of similarities to a board game, obviously.
Exactly.
Yeah, that's a question of manpower to implement. Yes.
Okay. Thank you.
So in both applications, you first at least trained your reinforcement learning in simulation. So did you make use of the fact that you have a model? So of model-based reinforcement learning? Or?
No, so the model is, so here there's not even a simulation going on. We never need to calculate the unitary. And in the other case, that's, so to speak, treated like a black box from the point of view of the reinforcement learning algorithm. And the only reason that we then cannot immediately do the same on an experiment is, of course, that in this first case that I was talking about is that we find that out-of-the-box reinforcement learning fails, and then we need to be smart about our input and about our reward, and that precludes a direct application. So then we had to introduce this trick of the two-stage learning.
Thank you.
So some more question. This is the last chance to ask the question during the school. One, Anya, at the end.
So I want to clarify a bit again. So we have the reward that it's the reduction in gate count, depth of combination, but what is the ultimate goal? Like, okay, we reduce this number of gates and try to do what with this specific circuit?
Oh no, so then we would run it, I suppose, on our quantum computer. And the fact that we have reduced the gate count just means that the overall error, the overall decoherence will be reduced, yeah? Because the application that we have in mind is obviously these NISC type devices. We don't have the amount of resources to really have an additional layer of error correction. So these are actual physical qubits. And we want to reduce the gate count as much as possible to run our little modest quantum algorithms.
Maybe I ask another one. Can this method tell us something about Cliffordness or non-Cliffordness level of the gate, the circuit that we've designed?
So the way it's set up, it's independent of that. So especially if you look at these circuits, they have parametrized gates, so arbitrary rotations, so it's not Clifford. I haven't really thought further about this question, whether having it Clifford would mean particular extra simplifications that I could exploit somewhere in the algorithm, for example.
Thank you.
Any more question? Okay, so if not, then thanks, Florian, warmly once more again. So now we will have small summary of the school with some awards. Yes, so so first of all, I mean, we are super grateful for our excellent lecturers. I think now, and invited speakers. I think now only Florian is here, but so maybe once more, thanks for the lecturers and invited speaker. Yes, the second group, very important, are tutors, right? So now let's thank to the tutors that spend their 2 weeks here tutoring you during hands-on sessions. I think that especially special thanks is to Anya, because as you realize, so I was giving money and decisions and authority, but in fact, Anya did lots of work, not only what she's supposed to do, like organizing the schedule and contacting speakers and preparing tutorials, but also she was a secretary of the school, organizing your hotels, flights, and so on. So I think she needs really warm thank you. So, and at the end, I thank you everyone. It's not yet the last word, but thank you everyone for coming for the school and actively participating. So I think that this was lots of activity, lots of discussion, and lots of interest in the subject. So I'm really glad that this school was I think from my side, my perspective, very successful. So you want something?
Well, yeah, I'm supposed to speak from. This is from part of everyone. We wanted to say thank you to you with this present. So, and,
So Anya, do you want to tell something? Okay, so now I think we can go to formal. Do we have next slide for? So I should, we should thank the providers of the money, right? So the school was financed by the Excellence Initiative that was given to our university. So your flight and hotel was supported by this. The conference dinner was supported by the Dean of the Faculty of Physics. The drinks evening was supported financially by my group resources, let's call it, right? And Machine Learning and Science and Technology Journal founded the awards for the best posters. So I think now it's time to reveal who is the winner. Yes. Yes, right, exactly. So Machine Learning Science and Technology Journal was generous to support the best poster award. So the first award is the open access waiver for publication in the journal. The second is £250 cash prize, and the third is the same. So, so somehow I think that everyone wants the second and third, because anyway your supervisors can pay for the first one, but you can put in CV that you were the winner. Okay, so now we can go like maybe the votes were like popular votes plus votes of the organizing committee, and that they were quite democratic in the sense. Yeah, the third prize, yes. We start from the third prize, and the third prize is for Rita. Yeah. Yes, so please, yes. So congratulations. We will contact the journal, so they will probably just send some access code.
Now
and
it's
we
just
will,
a promise of a prize.
Yes, and the diploma we will send in PDF, because I think no one really wants to now collect the pieces of paper. So, okay, so this was the third prize. Now the second prize goes to Koji Inui. For his poster on approximating fermions many-body wave function by feed-forward neural network. Yes, and the winner, the final winner is Kim. Yes. So for the estimation of thermodynamic observables in lattice field theories with deep generative models. So congratulations. Yeah, we will send the information, and I don't know, probably journal can ask about bank accounts for the third and second award. Okay, so once more, and we are very happy that poster sessions were really active. So not only during the poster breaks, but also during the lunch breaks, or even after lectures in the evening, there were lots of discussion there. So I hope that lots of new collaborations started, and this school will be very inspiring for the future collaboration. Okay, and now, right, so the very important thing is that we want to know what was good and what was bad in the school to make it better in the future, right? So this is the first summer school, like first scientific school I organized, Anya as well. So I don't know if Alex, this is first school for you, probably this one. Yeah, so Maciek did lots of things in his life. Yes, but I think we would be very grateful for all your comments and somehow rating different aspects. This will be also important for our university, and so don't worry to be harsh if something was bad, and don't afraid to be too enthusiastic. It was good. Okay, yes, it's anonymous, right? So we will not know who tell what. Okay, and the last thing. Yes, so now I think Anya continue as.
Thank you. Sorry, this just went down. Okay, so I will just touch on a few questions that I keep getting. So regarding attendance certificates, we will issue to all of you automatically Also to online participants who send us the posters and the flash talks and participated in hands-ons, I know who you are. So, and we have to then, we ask actually Darek asked one of our supervisor of PhD programs. So if you put the number of ECTS there, it's more welcome and easier than to like get your ECTS if you want from the school. So we do that. And we will send it in like next few days. Regarding the reimbursement of your travel costs, the people who didn't get it from us, take really this deadline, 9th September is important. Then I'm gone, and like yours, yes, your it's an uncomfortable situation. Okay. So yes, then if you need some confirmation of payment sent to me, it will be pretty automatically. So it's good. With invoices, it's complex right now if you didn't tell us before, but let's talk about it. And we're getting hands-on notebooks with solutions. We'll upload it soon to the GitHub. It will be cleaned. And again, thanks everyone who contributed to the tutorials and to the working on that and the lectures, and it was amazing. And finally, we had this idea of the lecture notes that participants do, and some lecturers already gave our blessing that they will look into it, including Florian. So today, 2:30, it will be like kickoff meeting. Let's say we will see how many people are really interested. And I mean, some people cannot participate because they are online already or left. But we will. This is just a kickoff meeting. It's not like, you know, some final declarations. Okay, and I think that's it from my side. Apart from, yes, I will also continue on what Michał said. I mean, I've been to many summer schools and we try to do like combine our experiences and do what we find is best. But I've never been to such an active summer school with so many questions, and like people just kept communicating, talking about science. It was amazing. And I don't know how much of it was COVID, like, you know, COVID related longing for other scientist contact, but apart, I mean, maybe it's just, you're just so amazing. So I think it's both. So yeah, really congratulations to you. Yeah. Yes, so thanks a lot.
So now we will have the last lunch, and then we will the school will be over, except the meeting post school meeting on notes. Thank you very much.
Just to say that before everybody's leaving, because we're discussing how to stay in contact, is the Discord going to remain open? Forever. Okay, good. Okay.